Hey guys, I'm Kevin. I work for a company called Consensus, and we build on the Ethereum blockchain. Can I just get a raise of hands to see how many people have heard of the Ethereum blockchain? Okay, basically 90 to 100% here. So that's really good. I'm really glad to see that you guys are interested and have heard about the technology. So we're here to bust a myth. So the myth here is that programming applications on the blockchain requires a PhD. It does not, and let's just build a simple application together and see how easy it is to build on the blockchain. So we're going to build on the Ethereum blockchain using smart contracts in a practical way, similar to how you would probably do something on the weekend or build something for a hackathon. Building on the blockchain, very easy. The tools are available to everyone. It's open source. Doesn't matter if you're a startup or an enterprise company, you're still going to be using the same tools. So having money doesn't actually allow you to really build a better application on the blockchain. And we're going to dive a little bit into use cases and see where the trends and where the market is going for blockchain applications. I'm sure you guys have actually probably heard of a dozen other presentations on blockchain that tell you what it can do, give you a little bit of background about it. But this presentation really is more technical. So if you're a developer, hopefully you'll enjoy it. We're going to actually write a smart contract at the end for about 20 to 30 minutes. So hope you guys enjoy it. Something that we're going to be covering today, we're going to take a peek under the hood of Ethereum and let you guys know how the cryptography and the mathematics sort of look underneath and what tools cryptographers are using to build the protocol level of the blockchain. We're going to go into blockchain applications. We're going to talk about the tools that you guys need to start building on the blockchain. And finally, like I said, we're going to spend 20, 30 minutes on writing our own smart contract. So peeking under the hood, we're going to go through three things today. We're going to talk about Merkle trees. So these are the things that actually make the blockchain very efficient. The Ethereum blockchain has been out for roughly 3 to 4 years. Can you imagine the size of all that data that's being stored on the blockchain since the beginning of time? A full archive node on Ethereum right now is roughly about 600 gigabytes in size. This is actually very, very small considering the amount of data that is holding inside an immutable distributed node. Generally, most of you guys, even people with laptops, probably have more than 600 gigabytes of storage right now. So 3 years of data living on the blockchain, only 600 gigabytes worth of data. If you do a fast sync, it's only about 80 gigabytes. We're going to talk about hashing and how hashing is used on the blockchain. And finally, signing transactions using private and public keys. I have a diagram here. This is a visualization on what a blockchain sort of resembles and sort of looks like. So you see the blocks up there? Those are what we call blocks in the blockchain. It stores a ton of information. Some important characteristics is the previous hash, nonce, Merkle root, and timestamp. It stores like probably 100 different attributes on top of this, but these are some of the more important ones. But if you look over here, the Merkle root, this is actually a very interesting application of a Merkle tree. Every block contains hundreds of transactions on the blockchain. And these transactions basically get hashed until you get a Merkle root. And having this Merkle root store all this information allows you to really create an efficient way of storing data. And we're going to go into a little bit of that later on. We're going to talk about the hash function. This is a fundamental piece of the blockchain. How many of you guys know what a hash function is? Can I get it? Hands? Okay, about 50% of you guys. So I like to use this analogy about a hash function. So a hash function is a one-way function that basically takes any arbitrary piece of data and outputs it into a fixed size string. So in Ethereum, it's generally 40 characters long. So it doesn't matter if you're storing a phone number that's 10 digits or a whole PDF file that's a couple megabytes in size. You throw it into this hash function, and you get a random 40 character string. An analogy that I use is you have a chicken, and you feed it through a hash function, you get a chicken nugget. But you can't put the chicken nugget into this hash function and get a chicken. So it's a one-way function that basically takes a bunch of data, feeds it through this really cool algorithm, and you get a fixed size output that makes the data integrity very, very strong, because if you change any piece of this input, the output will be dramatically different. So if you pluck a feather out of this chicken, you're going to get a different output in the hash function. And we're going to go into private public key cryptography. So when you are doing, when you have private public keys, this is a very fundamental piece of computer science. You use it every day, even though you don't know it. People with like GitHub profiles allow you to basically push your code into GitHub using your SSL certificates. This is using private public key cryptography. And in the blockchain, we use private public keys to sign information and decrypt information. So people sign information using your public key that's distributed to everyone, and you can read it by decrypting it with your private key. So one analogy that we use a lot is that you have your home address. You give this to everyone. People can send you mail. And when people send you mail, you're the only one that can read it if you have the key to your mailbox, assuming this mailbox is locked up. So private key, you keep to yourself, secure. Public key, you can share with everyone, and people use this to identify you. Digital signature. So digital signature is a combination of private public key cryptography and hash functions. Hashing information reduces it to a 40-character string, and then by signing this information with your private key, you can provably verify that this information has not been tampered with and that you have validated or you have attested to this information being what it is at that current state. If someone changes this information, people will know, and it will not actually show up that you have validated or confirmed this information, because it'll come out as a different hash string. So putting this all together, this technology, these cryptographic algorithms allow us to build really cool decentralized applications, what we call trustless applications on the blockchain. I like to give this diagram to people that are exploring the blockchain and think that they have an idea that's really good for the blockchain. So I ask this question, do you even need a blockchain? And I have them run through this exercise of putting their idea through this flowchart to make sure that they actually need a blockchain and the blockchain can actually help them achieve their goals. And if it actually fails this test, it'll probably point you to don't use a blockchain. I'm going to talk about native features of the blockchain. I have 5 of them here: immutability, cryptographic security, distributed ledger, consensus mechanism, and smart contracts. So immutability is, in the cryptographic world, they use this term, but really it just means that data is permanent and it can't be changed. Cryptographic security, you saw it demonstrated earlier, private public key encryption is built into the very foundation of the technology and the protocol that allows it to be very secure. Distributed ledgers. So this one's really interesting. It's generally what we call a unique source of truth, or the golden source of truth. You could always tell people to just look at the blockchain if they ever want to know if the information is accurate, if the information is up to date, because that is where everyone will go to verify if the information is correct. Consensus mechanism. So this is a characteristic where you have to have the crowd agree on a certain outcome or a certain characteristic before it gets put onto the blockchain. In the Bitcoin and the Ethereum blockchain, it generally requires 51% of the people on the network to agree that this is the next state before it gets put onto the blockchain. And Bitcoin and Ethereum use a proof of work algorithm. Ethereum is actually experimenting with proof of stake, which actually reduces the need for mining and all the heavy computation and electrical costs that is required of the blockchain right now. And finally, smart contracts. I'm not sure why they call them smart contracts. They're not particularly smart. They're actually very simple and uncomplicated programming code. You're going to see an example of it shortly, but I don't know why they call it smart contracts. It's really, like, you could probably call it a dumb contract, to be honest. I'm going to talk about some applications. So I work for a company called Consensus. We call ourselves a venture production studio. So we incubate companies within our own company. We have about 40 projects going on right now that build on top of the Ethereum blockchain. I'm just going to go over a few of them to just give you an idea of what we're looking at and what industries are interested in the blockchain. First one I want to go through is OpenLaw. So OpenLaw is a legal platform that has templatized very standard legal contracts into smart contracts. So this allows you to, instead of using a typical lease agreement, you could use a templated one on the Ethereum blockchain and basically sign your lease. Ujo Music allows music artists to actually control the rights of their data, or of their, I guess, their art. Downloading, streaming, and licensing is built into the platform that gives music artists more power to, I guess, allows more people to actually use their music without a bunch of like distributors taking cuts and eliminating a lot of middlemen in the system. Viant is our supply chain product. Supply chain is a very common use case in the Ethereum blockchain, or just using blockchain in general. It has a BPMN integration that allows people to actually create smart contracts without actually knowing how to code. Pangea, our real estate platform, it's a REIT on the blockchain. Allows you to invest, track, and trade tokenized property onto the blockchain. Virtual Poker is probably my favorite application of the blockchain. It allows peer-to-peer card shuffling and verifiable randomness on the blockchain, so you know for sure that the cards are random and you're going to get paid out if you win. Uport is our identity application. If you guys heard of self-sovereign identity, it's basically allowing you to own your data instead of giving it up to the Facebooks and the Googles of the world. Self-sovereign identity allows you to permission people to use your data the way that you want it to be used. So I guess you guys have probably all heard about the Facebook and the Cambridge Analytica scandal. Having self-sovereign identity basically allows you to really hold on to your data without giving it up to large companies to commercialize this data. We have Gitcoin, Grid Plus, Omega One. Gitcoin is a bounty platform. Grid Plus is an energy platform that allows you to distribute energy using an IoT device on the blockchain. And Omega One is a capital markets platform that allows you to trade large positions onto multiple exchanges. I won't go into those too much. I want to talk to you about smart contracts. Smart contracts are generally pretty simple. There's not a lot of logic to it. You really want your smart contract to be very, very simple in nature, because once you write your smart contract and deploy it onto the blockchain, it can't be changed anymore. There's no bug fixes. There's no upgrading your code. If you're using your contract to store Ether or tokens, and someone finds a vulnerability in your contract, they can siphon money out of your smart contract. So you really want to make sure that your contract is secure. And generally, the less code you write, the more secure and easily identifying the vulnerabilities it is. One general, I guess, I wouldn't say a rule, but a common way of people, when they write smart contracts, they generally get it audited by smart contract auditors, because you want other people that are experienced in smart contract writing to actually go over your code and make sure that you don't really have any general vulnerabilities in your code. It's similar to large companies doing pen testing. You want people to try to break in to make sure that your code is safe, so that when it actually goes live, someone else isn't breaking your code. We're going to talk about some development tools on the Ethereum blockchain. The first three on the left are actually consensus products. First one I want to talk about is MetaMask. MetaMask is a browser extension in your browser. It first was released on the Chrome browser, but afterwards it got ported to Firefox and a blockchain browser called Brave. Basically what it does is it's a hot wallet into your browser that allows you to do transactions on the blockchain with your applications with your web applications that you build. Infura is basically a sort of like your connection to the blockchain. If you want to build an application right now, you're probably going to have to spin up a node on your computer, wait a couple of hours to download about 80 gigabytes worth of blockchain data before you can start developing. What Infura does is that we provide this service for you where we expose our nodes through an API that allows you to connect to it when developing your application. So you no longer actually have to install and sync a full node before you can start developing on the blockchain. So it's basically an API that allows you to connect to the Ethereum network. Truffle is a development framework built for Ethereum, allows you to write, test, and deploy smart contracts. Very, very handy tool, especially if you're a beginner. They have a lot of tutorials that you can walk through to build your first smart contract. And Remix, one of my favorites, it's an online IDE for Solidity contracts. Allows you to write your code in the browser and deploy it straight from your browser. We're actually going to use this a little later on to write our own smart contract. I want to walk through the flow of how a developer would go about creating a decentralized application, more commonly known as a DApp or a DApp. So when you write your contract over here, it's generally a couple of lines of code. But when you're actually writing it, you're almost writing the documentation and writing your backend of your contract or of your application right into your smart contract. If you write it properly, it almost acts as an API docs for your application. You don't have to, spin up Swagger. You don't have to create your own server. No more Node.js or Express to deploy your backend. You write your contract, have it properly commented, which acts as, I guess, documentation, and deploy it onto the Ethereum network. So the Ethereum network is basically your infrastructure on the blockchain. Once you deploy it, you don't have to maintain it. You don't have to build a firewall. You don't have to do port mapping. You don't have to do any of that. It's exposed to basically everyone in the world. So if I deploy a smart contract right now, basically anyone with internet connection can connect to it, basically instantly. Don't have to spin up a server, so that's great. There are API libraries available in multiple languages, most popular in the JavaScript language called Web3.js. There's also Java, Python, and a bunch of other languages that allow you to connect directly to the blockchain and build applications for the blockchain. And of course, if you're a web developer, you can hook into these libraries. If you're familiar with React, Angular, Vue, Ember, Backbone, they all work really well with these libraries. All right, so we're going to go into writing our first smart contract. So I created this contract about a month ago. It was for an Ethereum meetup in Toronto. So our meetup organizer generally had an issue of people signing up for the event and only getting probably 70% of people attending the event. So sometimes we order food, we get drinks, we get a venue that fits, let's just say 100 people, and only 70 people come. So we have a lot of leftover food, leftover drinks, we have empty spaces that we could have filled up with maybe a wait list or something. So we wanted to tackle this with a smart contract. So I built something called an Rsvp contract. Basically what it does is it requires you to deposit a little bit of Ether to verify that you want to attend an event. So in this example, we'll use roughly $5 worth of Ether, so like 1% of the price right now, roughly $500 per ETH. And we're going to use like 0.01 ETH as the deposit that you have to put in. And if you come to the event, we're going to refund you this 0.01 Ether. So, and if you don't come, we keep it. We decide what to do with it, maybe pay for food, maybe donate it to a charity, but it's gone. You guys don't get it back. So it basically allows us to offer what we do for free, but require you like provide a little bit of commitment. And if you do come, you're going to get your money back. All right. I'm going to switch over here. Let me know if it's too small. I'm going to try to make it bigger. Can you guys see at the back? A little bit bigger? Okay. How's that? Okay, cool. So this is Remix. So the IDE, like this web page, what you see is Remix allows you to write Solidity code. It has a linter, it has a debugger built in. So if you're making mistakes, it'll prompt you. Also allows you to deploy the smart contract onto the network immediately. So I wrote this contract. It's roughly about 45 lines long with about 20% just like comments. So very, very simple code. So I'm going to actually just delete it. And we're going to rewrite this together. And then I'm going to walk you through the little nuances of like Solidity writing. So Solidity is the most popular programming language for smart contracts. It really takes inspiration from JavaScript, Java, or other object-oriented languages. So if you're a developer developing on JavaScript or Java or other object-oriented languages, it should look very familiar. Okay, so we're going to start. One thing that all Solidity contracts require is for you to specify the version that you're going to use. I'm going to put that. I'm going to type with one hand. And I'm going to do that. I have a piece of paper here. I'm cheating, but I hope you guys learn something from this. So all you have to do is specify progma, solidity, and your version of solidity. I'm using 0.4.18. Right now, the latest version is 0.4.22. You can see here. And I'm going to create a new contract. So I'm going to call it contract Rsvp. And then I have my little curly braces. So there's two variables I want to store in my contract. I want to store a minimum deposit, which is my 0.01 Ether that I'm going to put in later. And I want to store the variable owner. So owner is the person that actually creates the contract. So this is the only person that can actually refund your Ether. We do this because we're centralizing the authority here, but it's because we only want people that actually come to the meetup to be able to get their Ether back. If we didn't set up an owner, people can actually sit in their house and actually retrieve the Ether by themselves if we didn't specify this. So we're going to specify the contract creator as the owner later. So I'm going to create two variables. You have to specify the type. And it's basically an integer of 256 bytes. It's a public variable, and we will call it min deposit. So this is a minimum deposit, and I'm going to have an address, public owner. So these are two variables that I will have stored onto my smart contract. There's something called a mapping in Solidity that is basically like an array. It's like a key value pair array in your system. All right, so I'm going to create that, and it uses the arrow function. And we're going to use this array to store the balances of Ether that people deposit into the system. And then we have things called events. So events are interesting. So these are basically your logs for your smart contract. So when something happens and you want to store it in your smart contract, you generally push them into your events. And when you want to query your smart contract, you want to query your events as basically a log of everything that happens in your smart contract. So we're going to use this staked event when someone actually puts money or puts Ether into our smart contract, and we are going to record their address. Beneficiary. And so we're going to store who deposits the ETH and how much they deposited. Cool. You also need semicolons after every line. We're going to create another event called redeemed. So this is when someone actually retrieves their Ether. The event organizer gives it back to the original depositor. We're going to fire this event. Apologies for the slow typing. And then okay, cool. So we're storing these two parameters. All right, now we can start actually writing our smart contract. So we're going to write our constructor. So this is called only once ever, and it's only called when you create your smart contract for the first time. So it is always the same name as the contract itself. And then you're going to determine the arguments that you are accepting when the contract is being created. So when the contract is created, you're going to ask the creator, what do you want your minimum deposit to be? So as a rule of thumb, arguments in Solidity usually have a prefix of underscore, just so that when you're looking at the code, you know that this is an input that the user is providing when you write your code. There is basically an assertion. So this require function basically checks to see if any condition is met before you run the rest of your function. Basically, here we're going to make sure the min deposit is greater than 0, and it's not 0. And that's all. And if this condition is met, then the rest of the function gets run. We're going to set the owner variable to message.sender. Oh, sender. So, sorry. Okay, so there are a couple of special keywords in Solidity. Message.sender is one of them. So basically, this is the person that pushes the smart contract onto the network, and we're setting the owner as the person that submits the smart contract. And we're going to put min deposit is equal to the input min deposit. So this is the variable that's inside the smart contract is being set as the argument that's passed into the contract. All right, so we're done with our constructor function. The next function is basically a fallback function. Function. So if you don't put a function name and you put just the brackets, it becomes a fallback function. So this is basically what gets called when you send Ether to the contract. So by default, the Ethereum blockchain allows you to send Ether to either personal addresses or contract addresses. And contracts almost behave the same way as a personal address, and it can hold Ether. So function external, so this is an external call, and you have to use the payable function, or the payable keyword, if you're sending Ether. And we're going to create a function called Rsvp. Basically, this Rsvp function is called when we send Ether to the contract. And it's an internal function, and it can't be called outside of the contract. All right, so what do we want to happen when the Ether is being sent to this contract? We want to make sure that whatever they send is greater or equal to the minimum deposit. So if we set the minimum deposit as 0.01 Ether, we don't want them to send 0.001 Ether. So we're going to do a require message.value. So this is another keyword that is greater or equal to min deposit. So this checks that what you're sending is greater than the minimum deposit. We're also going to set the balance. So this is the mapping that we set earlier. We're going to update it with message.sender. So we're saying the key value pair, where the key is the address of the sender that's sending the Ether, to message dot. Actually, we're going to make sure we increase it. Sender plus message dot value, in case they sent it twice. We want to make sure we capture that. All right, and finally, we're going to emit. So emit basically fires the event that we created earlier. So we're going to fire the staked event. and we're going to pass in what we want to store in the event log. And we're going to pass in message.sender and message.value. So if anyone wants to query what happened in the blockchain in a later point in time, they will query the staked event log. And then finally, we're going to create a refund function. Refund. And where is it? Okay. It's a public. And the refund, we're going to have an argument that we're going to take in called recipient. So basically, the refund function is only called by the person that created the contract. So generally, this would be the event organizer. So we want to require that the owner is the same as message.sender here. And if anyone else tries to call the refund function, it'll fail. And only the person that created the contract, generally the meeting organizer, can actually call this function. We're actually going to require another case, and it's that the recipient is not equal to address 0, because this is more of a security case. Make sure that address 0 isn't the one that's calling it, because it can get dangerous if address 0 is calling the contract. Okay, so we're going to do recipient.transfer. So transfer is a special method within Solidity that actually allows the contract to send Ether. So if you do the type for this variable is an address, so it allows any address to transfer Ether from the contract to anyone else. So we're going to do recipient.transfer balances, and the recipient. So this is, we're grabbing the value of the Ether that was stored in the mapping for this particular recipient. And we're setting that to the recipient. And we're going to emit an event called redeemed. So this is the event that we created on line 10. Not require. Redeemed. And we're going to put in the recipient and the balances of the recipient. Cool. So the event is fired, and we update the balance of the recipient to make sure it is zeroed out, so that their balance is no longer whatever it was before, because they have taken the balance out of the contract. All right, so this is basically the contract that we need to offer the functionality that we want for the meeting organizer. So Remix, really cool. It actually auto-compiles your contracts to make sure that you don't have any bugs. And if you did have a bug, if I miss a semicolon here and I press compile, it'll tell me that I need a semicolon. And I compile it, and it's good. These are just general warnings. So what I'm going to do here, I go to the Run tab, and it actually allows me to deploy my smart contract onto the Ethereum blockchain. Behind the scenes, it's actually running Infura, so the API gateway to the blockchain that I was talking to you about earlier. It had a little orange logo and looks like a Japanese word in the middle. So and I also have MetaMask here installed as a Chrome extension. So my MetaMask is connected to the Rsvp testnet. So Ethereum has a couple of test networks. Rsvp is one of them. I have a couple of or 0.38 Ether here, and it's fake Ether. It allows me to test my contract on a live network that people are running in the real world that simulates the main network. So I'm signed in here, and I want to basically deploy this contract. And I'm going to have to set the minimum deposit because this is the argument that's being requested as part of the constructor. So Ether actually is divisible by 18 decimal places. So if I put 1, it's actually equivalent to 1 over like 1 and 18 zeros behind it. So what I actually have to do is specify, if I want to do 0.01, is actually 16 zeros leading up to the value that I want to. So we're going to count to 16 together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Okay, so we have 16 zeros. So this is equivalent to 0.01 Ether. I'm going to click Create. You see this little 1 here. It pops up in my MetaMask account and it basically asks me, do I want to deploy this contract? Is this what I want to do? The cost of this contract is denominated in, let me see here, maximum transaction fee. So the more complicated my smart contract is, the higher the fee it is to deploy this. So what you're really doing here is you're paying for the infrastructure cost of actually pushing this contract to every single node on the Ethereum network. And it'll basically cost you 22 cents to do that, to put it onto every computer on the network right now. All right, we're going to do it. And we're going to push it onto the Recipient network. So there's a cool site called Etherscan that allows you to take a peek into the blockchain. It tells you what your transaction looks like and what state it's in. So right now it is pending. The Ethereum blockchain generally takes about 15 seconds for it to push into any block. So it's not a continuous system. It only updates itself every time a block is appended to the blockchain. So transactions can only be included every roughly 15 seconds. It's probably taking me a couple of blocks to get this transaction in because of the load of the network. And sometimes Etherscan is a little buggy too, and it doesn't update as fast. But I'm going to refresh it a couple of times. But if I wanted this transaction actually to process quicker, I can up my gas price of the contract, where I'm paying more fees to have it bumped up in the queue. But I'm cheap and I don't want to spend all my Ether, so I'm going to only put 1 GWay, which is probably less than a cent. All right, so it's completed and it's pushed onto the network. And this is the contract address over here. So if we go back into our remix, we're allowed to interact with this contract right in remix. So the owner is set as this account owner right here, 0xEE2DE, and a bunch of other random strings at the back. I'm gonna actually I'm just gonna copy this contract address, and I'm gonna log in with a different MetaMask account. I'm just gonna move over to another one here, and I have another MetaMask account. What I'm doing here is I'm simulating a typical user, a typical person that wants to register for the event. So in this account, I have 1.7 Ether, and I'm going to send it to this contract address that was just populated on the blockchain. So this is the contract address of the Rsvp contract that I just deployed onto the Recipient network. And I'm going to send them 0.01 Ether. So MetaMask is a little smart. It doesn't take in 18 zeros. It actually converts your denomination into proper decimal places. And I'm going to send 0.01 ETH to this contract. And Over here, it tells me the cost of it. Actually, what is happening here is I'm sending 0.01 Ether, and it's only costing me 3 cents to send it. Like, this is generally not a lot of money, but if you're doing microtransactions, it could add up. So depending on your use case, you want to make sure the transaction cost is generally fairly low. And we're going to wait to see this contract or this transaction push through. Again, could take about a minute, as fast as 15 seconds.
So once that transaction goes through, the value is transferred to
the contract.
So
yeah.
the contract owns the value.
Yeah, exactly.
And it's implicit in there. We saw the transfer
Yep.
very explicit, but this one is not actually written out as receive. It just happens.
Yeah. So basically, what happens in this? Let me switch back to my other one. So what happens here is actually calls this function when you send Ether to it, and this function is telling it to run Rsvp, which is an internal function, which is this. So just make sure the minimum deposit is met, and it actually updates the balance with your address on it to just keep a record of how much you've deposited into this contract. So it allows us to remember how much we have to refund you afterwards.
So in this contract too, since the contract owns it,
Mm-hmm.
and there's no way of getting money out except by refunding.
Yep.
If you don't refund, it's lost.
It's locked into this contract, and it's owned by this contract.
And so
Really.
you can basically, unless you wrote it properly, it's stuck there now.
Yeah, yeah. If you didn't write this refund function, it is permanently going to be stuck into this contract.
Well, even if you don't refund. Then
Yeah, if you don't refund, then it's locked in there until you refund it. But if you didn't actually write this refund function, it will be permanently locked. There's no way for you to actually retrieve your Ether. Does that make sense?
Well, yeah. So let's say in the case of your conference get together,
Yeah.
no one came, and so you don't want to refund it to anybody.
Yeah.
In this contract, you can never get that money out again.
You can, in this contract, what the meeting organizer can do is that they can refund it to themselves.
Yeah, but they check to see who the balance was from.
So, yep. So, really, so this refund function is very generic. It actually allows the meeting organizer to specify who it wants to refund. But oh, actually, you're right, because you actually you can only refund the balance to that person. It's actually going to be locked up. You're right. Actually, you're right. I can't actually refund it to myself. It only goes back to the original person. So if I could write a function that allowed me to do that actually, to actually refund myself. So to the people online, we're just talking about what happens if, I guess, if no one comes, is the funds permanently locked into this contract? In this case, yes, actually. Unless the organizer is nice enough to refund the funds back to the people that didn't come, they can actually take the funds themselves. Right. All right. So the transaction actually went through, and if we actually look into this contract, you're gonna see 0.01 Ether was sent to it from another contract that we sent about 2 minutes ago, just before our conversation over here. So we see that this contract actually has the Ether balance of 0.01. So what we're gonna do now as a meeting organizer, it's the day of the event. I am actually gonna refund this person. So they just have to provide their address. They can provide it through a QR code, generally the way that people transfer addresses, so you don't have to type them. And I could actually use Remix to do that. So I am going to refund this user. I'm just going to click this button. It's going to prompt a MetaMask transaction. It'll cost me 2 cents to do the refund, but it's worth it for me as a meeting organizer to make sure that you come. Paying 2 cents is generally not too much for me. All right, so this transaction is being published onto the network. You can see that it's calling the refund function over here. And if we go back to the other account, I guess right now it has 1.7. Oh, we just saw an update. So it was at 1.741 Ether, now it's 1.751 Ether. And if I really wanted to verify it, I could look at my account on Etherscan. I have a lot of test code here. And it's 1.751, which is my original balance. So if we go back to the other screen, we can actually see that the contract no longer has any Ether because they refunded the original user. So this is a very, very simple contract that allows people to hold Ether into a contract and write, I guess, sort of like business rules around how they want the contract to execute. And we did that in about 20 minutes, which is actually incredible. Anyone can use it right now. Front-end developers will probably create a nice GUI for this contract. You can do it in React, Angular, Vue, whatever you want. You just have to plug into the JavaScript libraries, and you have your application. Yeah, and that's the end of my presentation. Anyone have any questions? Yeah, go ahead.
Okay, so most of the stuff that's stored in Ethereum is data. It's fixed stuff. But the contracts, how are they represented in Ethereum, and how are they validated so that you can know this thing that's sitting in Ethereum is exactly the contract that I thought I wrote?
Yeah, so the question is, how does the Ethereum protocol validate what the contract is? And I am calling what I think is being called. So really cool, actually. This is actually what the code looks like on Ethereum.
Oh, that's perfect.
Yeah, it gets compiled down to bytecode, and it's just, it's jumbled up. If you're like a forensics expert, you can probably actually put this back together into the actual code. But one of the issues is that you won't know what the variable names are unless it's published. And it's really hard. It's basically you're just guessing at that point. So it's really hard to do. So what happens is that people actually publish their contracts onto, like, let's just say GitHub, and this site allows you to verify and publish your code. So what it does is you can paste your Solidity code here, and what this website does is that it actually compiles it back down to bytecode and compares if this code is the same as the code on the blockchain. If it's a perfect match, it'll actually say that this has been verified and published onto the blockchain, and people can actually know and verify that this is actually the code that's being run on this contract. So basically, it requires the developer to be transparent, and if the developer wants to be transparent, they just publish the code, and if you want to verify it, is you take their Solidity code and you compile it down to bytecode and match it to see if it's exactly the same as the one on the blockchain. And if it is, then you know for sure it's basically what you're running. Does that make sense?
Yes.
Okay.
So the second half to that question
Yep.
is, how do you verify the blockchain, whoever's running the code is actually running the code as you expect it to run? What verification do they publish to show that they're actually doing the correct execution of the contract?
So the question is, let me get this correct. Is the user actually running the code the way it's supposed to be run?
Is the blockchain, whoever is creating the next thing, how do you verify that they're actually correctly executing the contract?
When you say they, who do you mean?
Whoever creates the entry in the blockchain that represents the execution of the contract. How do you know that they're actually executing it correctly?
So the contract is the contract. When it gets published on the blockchain, it'll behave exactly the way it's written.
How do you know that part?
Well, it's literally the fundamental of code. Like, it won't do anything that you don't tell it to do.
Well, the blockchain itself isn't executing the code. There's something that executes the code. What guarantees that they're executing it faithfully?
So the blockchain, So your question is, how do we verify that the nodes that are running the Ethereum protocol are actually running the smart contract code that's written onto the blockchain and not something else? Is that correct?
Yeah.
Okay. So the protocol itself guarantees that. You can't actually change anything in the blockchain. You can't actually run code that's not there. You're actually just running whatever is on the blockchain. And using consensus algorithms, you can actually verify that people are being faithful. If one person is running something different from everyone else, then everyone, like the consensus is that generally everyone else is right. Unless you have 51% or more people running, I guess, malicious code, then they'll generally run the way it's supposed to run. Yeah. Any other questions? Yeah, over there.
Verify the identity of the contracts. If I create one contract similar to what you have, and I say my contract instead of your contract you use it, how can I verify that money is according to my contract instead of your contract?
Yeah, so the question is, how do I verify the identity of the contract and make sure that people are using my contract instead of someone else's contract where they might have changed like one variable and it could have been, let's just say, malicious or whatever. Or it could be the same thing.
The phishing contract.
Yeah, the phishing contract. So the contract addresses are all different. So if I deploy it right now, I have a contract address that is 0x7ED7823 and so forth. When you deploy it, it's going to be totally different. So what you want to do is basically tell people to use this particular contract address. This particular contract address is the identifier for this contract that's deployed onto the network. Nothing else will run on this address. If you give someone else a different address, it's going to run on that contract. So you actually see a lot of these cases with especially token sales where people say, oh yeah, invest in our token sale, and generally they publish it on their website. But on Slack channel, people want to like fake, or they're trying to fish, and they paste a different contract address and tell people, yeah, this is actually the token sale. Go here and deposit your funds over here, which is the one that they have control of. So you really want to verify that the contract address is right before you send any money to that contract address. Does that make any sense? Or does that make sense to you?
Yeah. I'm just thinking of the users. You have to put a UI in front of it. You can't see that.
Yeah, so your typical user will probably never see the contract address itself. So we've seen people actually steal DNS domains, and then if they have actually access to like a legitimate company's domain, and they can change the contract in the UI, and like people are actually going to actually send their funds to that. So that's actually one area that you want to protect against as well, is that your front end is protected so that the users don't actually send it to the wrong address. Any other questions? Yeah, we have one in the back.
A very interesting part beyond deploying example when you deploy smart contract, you want it to be parameterized in a way that you can ensure longevity. Once you release it, you'll be able to change the deposit or whatnot, and you'll be able to speak to what are the best practices for deploying contracts that you want to actually use this forever.
So the question is, if you're running this in production, you actually want your contract to be upgradable. You want to add new features to it. You want to, if there's a bug, you want to be able to fix it. So I'm probably going to speak to that question in more of an upgradable smart contracts sort of terms. So there's probably like 2 or 3 different ways that you can make your smart contract upgradable. So what you could do is have a proxy contract. So one contract, basically, all it does is store the data for your smart contract. So all it does is have variables and like mappings and events, and probably just like one function that points to another contract in the future that you can actually upgrade. So you have one function that says, do whatever and do the business logic in another contract, data stays in the first contract, and you write another function in the first contract that allows you to change that contract address that has all the business function. So you separate your business function and your data. Your data lives in one function, and your business logic that's upgradable lives in another contract. And every time you want to change your business logic, you just tell your data contract to point to a new contract with your new business logic. Does that make sense? Yeah. Yeah. So the comment was that does this, get away from the idea that the blockchain is immutable? I generally like to say no, because the data will still be the data, and people can see a transactional log of how that data became to be at the current state, and you could actually run through all the past transactions in chronological order to see what happened at every different point in time. So if they saw that you upgraded your contract on January 1st, they can actually have a look at what the previous contract was and basically rebuild the state at different periods of time. I think that's probably the best way I can answer it. It doesn't, I guess, if you're already ready the contract to be upgradable, like you're already accepting the fact that you're allowing the contract to change, and people should understand that. Cool. All right, I think that's the end of the presentation. Thank you, guys.